All right, so for this next part of chapter 4, we're going to be talking about some radical mechanisms. And in particular, we're going to be talking about halogenation reactions, right? So reactions involving halogens. And as you can see from this first example here, right, when we take methane and chlorine, right, just Cl2, and in the presence of light, remembering this H and U term, we see something interesting. We see a sort of substitution happening, right, with a hydrogen and a chlorine. And looking at the products, we no longer have methane, but we have chloromethane and hydrochloric acid, right? There's been a substitution that takes place, right? And this is what happens with these radical reactions is essentially one atom on our carbon molecule gets replaced by a halogen, right? And vice versa. The hydrogen goes onto the other chlorine portion of Cl2. And this can keep happening when we have chloromethane now as a reactant. We can keep exposing it to chlorine and light, and we see that there's more and more substitution reactions happening, right? We're getting more and more chlorination, right? More and more halogenation of the initial molecule, right? That initial methane, right? Left to its own devices, methane will go right to the totally chlorinated version, right? Tetrachloromethane at the end here. Now, what exactly is happening in this process, right? How is one atom seemingly moving to the other molecule while the atom here moves to the initial carbon molecule, right? How does the substitution take place? And the way we talk about that is through something called a mechanism. And I've mentioned this term before, right? Talking about arrow pushing. But in the case of a radical reaction, for a mechanism, we have a initiation step, right? As you can see below. We have a propagation step, and we have a termination step, right? There's three different things kind of happening in a radical reaction. And we'll go through each of these, right? Remembering that we're starting from methane and Cl2 and going to the end, right? So just so we're all on the same page here, right, we're looking at this reaction here. Right? How do we get from those starting products to the end? Right? So the first thing that happens is we have our initiation step, right? And as it says, this generates a reactive radical intermediate. And kind of like we've already discussed, right? I think I used chlorine as the example. What happens here, and we have to use arrow pushing, right? So the mechanism's arrow pushing has to be shown. We get the homolytic cleavage of the Cl2 bond, right? And again, we're using single-headed arrows to denote that one electron is moving from its origin, right? So we have two electrons in a covalent bond. One electron is moving onto one chlorine, and the other electron is moving onto the other chlorine. So we have our two radicals here. We don't need to show lone pairs for these, but I'm including them all so you can see what's happening, right? And remember that, right, there's only 7 electrons here, not an octet. So even though there's no charge, chlorine is electron deficient, right? It wants another electron to fill its octet. And that's why these radicals are so reactive, right? Even though they're not charged, that lone electron is ready to pair up, is ready to do something to get its octet filled. So next, after the initiation step, we have the propagation step. Okay, and what happens here is the radical, right? That radical we generated, the chlorine radical, reacts with a stable molecule to form a stable product and another radical intermediate. Okay, so usually with propagation steps, there's more than one thing happening at a time. Right? And the key word here is propagation, right? So even though we're reacting a radical with something, we always end up with a radical so that this process can continue in some way. So for this specific example, right, we formed our chlorine radical. And so remembering we have methane left to deal with, right, how does this happen, right? How do we go from that methane to chloromethane? So in the propagation step, we have one electron, right, coming to form a bond with hydrogen, right, that hydrogen atom. And again, there's only one electron moving from that CH bond, so the other electron has to be moving onto the chlorine. Okay, you see that? So we have this new bond formed here, right, and I'll highlight that in blue so you can see where it's coming from. Formed between the hydrogen here and the chlorine radical. And there's no longer any radicals left because one electron from hydrogen, one electron from chlorine, we make our covalent bond, but now we have a methyl radical, right? So this is ready to propagate, right, to continue to react. And so, for the second propagation step, okay, we end up with our final product, right, that chloromethane. And so to do that, right, same as above, that one electron comes in, the chlorine molecule breaks to form that bond with the methyl radical, and this other unfortunate chlorine ends up getting the lone electron, so now we have a chlorine radical again. Right, so we've now formed this bond between carbon and chlorine. And importantly, right, we only show propagation steps that form a new product, so we wouldn't want to draw further propagation steps that result in things we've already seen. Okay, so I'm only showing these two propagation steps because these are the only two things that are happening, right? We react to the chlorine radical we made with methane, form methyl radical, the methyl radical reacts, right? We wouldn't show the methyl radical reacting with methane, right? Because we would just end up with the same products. So we have to show the methyl radical reacting with Cl2, because not only do we end up with a chlorine radical to continue propagating, and we end up with our new product, right? But the chlorine radical, we can say, moves on to continue propagating the radical reaction, where the chlorine radical is now free to continue to react. And so when does it all end? And that comes from the termination step. And these are side reactions from two radicals reacting to form a stable product, right? Because once we have two radicals reacting, the reaction is over, right? It can no longer continue. Kinetically, there's not many radicals in a solution at a time, so the chances of terminating are a lot lower. It's more likely the radical will react with a stable product. But eventually the radical reaction will end when it comes into contact with another radical species. Right, if you remember from the propagation step, we only had two radicals that we were making, the chlorine radical and the methyl radical. Right, so this is just every single possibility of that reaction. Methyl radical with a chlorine radical with itself, and methyl radical with itself. Right, again, if we were to show the reactions happening, right, it would just be with the single-headed arrows showing the end terminated product. Okay, I hope that makes sense. We won't typically have to go into this level of detail, right, with doing radical reactions. We can typically just look at the reactants and presume what the major product would be. Okay, I might ask you to do the initiation, propagation, termination steps, but we can certainly just look at the reactants, not worry about the actual mechanism, and just come up with the product. So importantly, I've been doing all these examples with chlorine. There's a big difference between chlorination and bromination, and I kind of alluded to that, right, when I showed you methane, and you ended up with a totally chlorinated product. Chlorine is a lot more reactive, and I won't go totally into the kinetics of this, but essentially the chlorine radical is smaller, right? So if we have a chlorine atom with a radical, right, it's a lot smaller, so it's going to be a lot more reactive, right? Very similar to acid-base rules, as opposed to bromine, right, which is a larger atom. And even with the bromine radical, which again, bromine larger than chlorine, thinking about it in terms of, kind of like conjugate base rules, right? The larger atom is going to be more stable, so it's not as reactive. You see here with these two examples, right, our halogenation, our halogen species with light forms a radical. With chlorine, propane gets totally halogenated, but with propane and bromine, we only see bromine in this one spot. You might be wondering, why does bromine go in the middle of propane, right? So we have to remember our rules for radical reactive species, right, with carbon. We have to remember that, right, if we're looking at propane here, and we say that the radical is on this secondary carbon, right, we have to remember that's more stable than the radical on the end carbon, okay? And I'm kind of skipping over like the initiation and propagation steps, but eventually we would get here, right? Because there has to be a radical formed to react with radical bromine. So remembering that secondary radicals are more stable than primary radicals, we know that the bromine radical will react with propane in the central carbon position to get 2-bromopropane. Okay. So what we'll do in class is we'll do a couple examples of trying to figure out where the halogen species will end up on our reagent. Okay. So you have two here. Try to do them on your own and see what you can come up with. Again, you don't need to worry about doing the mechanism for these. We'll do it in class. We'll do one of these reaction mechanisms in class, but you can just worry about what are the products, okay? You have to think about what the radical intermediate species will be, right? Remembering these carbon radical stability rules. So that'll be important, okay? And again, right, bromine is going to be our radical halogen species. Here, looks a little different. This is something called NBS, N-bromosuccinimide. And here you just have to worry about bromine, right, being the radical species. The rest of this, right, the succinimide portion, you don't need to worry about. Okay, so take a crack at this and we'll talk about it during class.